Okay, we're back in section 5.2. This and then section 5.3 is the last one. And now instead of graphing just one inequality, we're going to graph a system, which means two inequalities. And the examples I'm going to be using will have these non-negative restrictions, x greater than or equal to 0, y greater than or equal to 0. So, non-negative restrictions. Only, our graphs are only be in the first quadrant. So what we want to do is graph these two inequalities, 2x plus 3y is less than or equal to 6, and x plus 6y is less than or equal to 8, and then find all the corner points. And once we see what the graph looks like, then we can define what we mean by a corner point. So, graphing 2x plus 3y is less than or equal to 6. How do we graph that? Find the x-intercept, right? And that'll be 6 divided by 2, so that's 3. Find the y-intercept, that's 6 divided by 3, that's 2. So again, to find the x-intercept, you set y equal to 0 and solve for x. Right? And if you set y equal to 0 and solve for x, you get 2x equal to 6. To find the y-intercept, you set x equal to 0 and solve for y. And if you set x equal to 0, you get, from 3y equal to 6. And so that gives you the y-intercept of 2. The other graph is x plus 6y equals 8. What's our x-intercept? Again, set y equal to 0, so you just have x equal to 8. And the y-intercept, again, you set x equal to 0 to find the y-intercept, so you have 6y equals 8, and so that's 8 over 6, which you can simplify to be 4 over 3. So it gives me my x-intercept and my y-intercept for both of our two inequalities, and this is an inequality, so we'll make that a less than or equal. But the border of the inequality is this line, so you find the x-intercept and y-intercept of the line. Okay, test point. Right? We know one side of the line is the less than side, one side of the line is the greater than side. Which side is which? Well, use 0, 0 as your test point. 2 times 0 plus 3 times 0 equals 0. That's less than or equal to 6. This is true. So, what does that mean when you plug in your test point and you get something true? That means you shade the side 0, 0 is on. Right. So 0, 0 is on the less than side of 6. And again here, what's my test point? 0, 0. Plug that in, you get 0 plus 6 times 0 equals 0. So plugging in 0 for x, 0 for y. And that's less than or equal to 8. And that's true. So shade the side 0, 0 is on. So, to graph this, what do I need? I need an x-intercept of 3, y-intercept of 2, an x-intercept of 8, and a y-intercept of 4/3. Only the first quadrant, so I don't need to have any kind of negative things going on here. So, we'll put my origin here. 2, 3, 4, 5, 6, 7, 8, 9, 8 here. 2, 3, 4, 5, 6. So 8 is there. The y-intercept is 4/3. If this is 1 and this is 2, 4/3 is 1 1/3, so it's about there. And you know, it's not an art class, so you can just sort of sketch it freehand. That's the line x plus 6y equals 8. Right? X-intercept, y-intercept. X plus 6y equals 8. We leave it solid because it's a less than or equal. For this line, again, this is less than equal, so we leave it solid. X-intercept is 3, y-intercept is 2. 1, 2, 3. There's my x-intercept. Y-intercept is 2. That's here. So it goes through these 2 points. And we'll just sketch that out. And then it should go through there. Okay. So, for this line, y equals 2x plus 3, y less than or equal to 6. We need to shade the side that 0, 0 is on, so that's this side over here. For this line, we need to shade the side that 0, 0 is on. So that's over here. Right? So let's do some extra colors. We will, pull in, we'll go red. So the side we want to shade for 2x plus 3y is less than or equal to 6, that's red, is this side. It's this side of this line. And we'll go, what other options do we have? Ooh, blue. We'll go blue. So this is the blue one. So we shade this side of this line. To get both this and this, that means we're looking for the overlap between the two. So that's just this part down here. This part is blue but not red. This part is red but not blue. This part up here is neither one. So both, we should have, say, green. It's just this part that is the area that we want. And why just in the first quadrant? That's from my non-negative restrictions. Right? So that's my shaded in part. Okay, so if I give myself a little bit more space here, what's my insert? Insert space. Come down here a little bit. We can draw the same version, but a little tidier now. Go back to my black pen. So what we have is one line, 1, 2, 3, 4, 5, 6, 7, 8, with intersects at 8 and 4/3. So that's x plus 6y equals 8, and one line with the intercept at 3 and 2. So there's 2, and there's 3, and so this line is 2x plus 3y equals 6. And what we found that the region that we're interested in, if we go back to our green pen, is this one. Right? Because it's on the correct side of both of the two lines. Now, what are the corner points? Now, there are 4 corner points, right? One is here, that's one corner. This is another corner. This is another corner, and this is another corner. So 4 corner points there. It looks like we'll need even more space because we'll have to do a little bit of calculation. So what are these 4 corner points? Well, some of them we know. This one is the x-intercept of 2x plus 3y equals 6. So this point is x equals 3, y equals 0. This point is x equals 0, y equals 4/3 because it's the y-intercept of this line. And this, of course, is the origin, 0, 0. Note that this point is not a corner point of the region that we're interested in, right? This is an interesting point. It's the y-intercept of this line, but it's not one of the corner points here. It's not on the boundary of this green region, so I don't care about it. What's that point? Well, this is the intersection of my two lines. So we need to find out what the intersection of this is. To find the intersection, we'll use something called the matching coefficients procedure. Match coefficients. So what do we have? We have 2x plus 3y equals 6. These are our two equations. And x plus 6y equals 8. So multiply this one by 2. And what does that give me? It gives me 2x plus 3y equals 6, because that's my, I didn't do anything to the first equation, but multiplying the second one by 2 gives me 2x plus 12y equals 16. And what we've done here is, by multiplying by 2, we have matched the coefficients on x. Right? And why is that useful? Well, if we match the coefficients on x, then we can subtract the top equation from the bottom equation. Oops, I don't want to do that. We can subtract the top equation from the bottom equation, and then that will allow us to, I'm not happy with this at all, solve for y. So let's see if I can get this insert space thing to work properly. It keeps moving up there like that. Okay, that seems to be okay. So we'll subtract the top from the bottom. Oops. That's not erasing now. Subtract top from bottom. Right. 2x minus 2x is 0x, so I don't need to write that down. 12 minus 3 is 9y. 16 minus 6 is 10. So y equals 10/9. Once I know y, you can plug that into either original equation to find x. So if we plug it into this equation here, x plus 6 times 10y, x plus 6 times y equals 8, but y we know is 10/9, and so this is x plus 60 over 9 equals 8, which means x equals what? 8 minus 60 over 9, but 8 we know is 72 over 9 minus 60 over 9, so that's 12 over 9. And if we divide top and bottom by 3, just cancel out those 3's, that becomes 4/3. So, oops, that's a little messy. Let's try it like this. Y equals 10/9. X equal to 4/3. That's my intersection. Right. And so now we know the 4 corner points. Okay, so matching coefficients is a little quicker than solving for the intersection by setting the equations equal to each other or something like that. And so we sort of like that. So here's a similar problem. Graph the system of inequalities, find all corner points. 5x plus 2y is less than or equal to 20. 4x plus 3y is greater than or equal to 24. X greater than or equal to 0. Y greater than or equal to 0. We recognize this immediately as our non-negative restrictions. I don't need to graph them. It just means my graph of this has to be in the first quadrant. 5x plus 2y less than or equal to 20. To graph this inequality, what do we need? We need the x-intercept, which is going to be 20 divided by 5, which is 4. We need the y-intercept, which is 20 divided by 2, which is 10. Test point. 5 times 0 plus 2 times 0 less than or equal to 20 is true. Shade, side, 0, 0 is on. Excellent. What about the other one? 4x plus 3y is greater than or equal to 24. 4x plus 3y greater than or equal to 24. To graph that, what do we need? The x-intercept, 24 divided by 4 is 6. The y-intercept, 24 divided by 3 is 8. And our test point to figure out which side we have to shade, plug in 0, 0. So 4 times 0 plus 3 times 0 less than or equal to, greater than or equal to 24, sorry. That's false, because this is 0, 0. So shade the side opposite 0, 0. We don't want 0, 0 on the shaded side. Great. So, with all this information, now we can graph these inequalities. I'm going to need more space. Somehow I put out my space, and it almost seems like I've got plenty of it, and then never do. That looks a lot of space, though. Okay, so what does our graph look like? Let's see, if we want this to be 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. So there's 0, and we need to go out to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, say. And there is our graph. The first line, 5x plus 2y less than or equal to 20, x-intercept of 4, y-intercept of 10. 1, 2, 3, 4 is here, and 10, like we said, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is up there. So this should go through there, but close enough. And we shade the side that 0, 0 is on. So we're going to shade over here. So we'll put a couple of shading marks in there. Actually, what the heck? It is a computer. I can do all sorts of other colors. So we'll put in some red here. So we want this side from this line. Okay, so now we'll go back to black and say, graphing this one, we want x-intercept to be 6. That's there. Y-intercept to be 8. That would be there. And we can graph in that line. And we want the side opposite. So from this one, we want the side opposite. So we can go to my pen and say blue. And so for this line, we want all that area. So what's the area we want that is in both? Well, that's just this area up here. So let us, oops, let's not do that yet. What area do we want? Well, we can get rid of all these, hopefully get rid of all these blue ones. Boop, 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 boop. Now that we've identified what area we want, get rid of the red. And we'll put back in our y-axis, and we'll shade in green the area that we want. So we want this area here. That was on the correct side of both of them. What are the corner points? Well, we know some of them. Right? This is 0, 10. That's one corner point. This corner point is 0, 8. And we want to know what's that one. Those are the only 3 corner points of the green region. There are these 2 points down here, but I don't care about them. So what corner point is that? Well, same procedure to find the point of intersection of these two. (5x plus 2y equal to 20), 4x plus 3y equal to 24. And again, I want to match coefficients. It's a little bit tricky here because, you know, the numbers are all sort of prime to each other. But first row times 3, second row times 2. If I do that, multiply these two by each other, then my y's will match. So I get, having done this, I get 15x plus 6y equals 60. And the second row by 2 gives me 8x plus 6y equals 48. And then I can subtract. Now what does that give me? 15x minus 8x is 7x. 6y minus 6y is 0y. 60 minus 48 equals 12. So that gives me the x coordinate, 12 over 7. And I can plug it back into one of my original equations to find y. And I will plug it into this one. So plug this into the equation 5x plus 2y equals 20. So if I plug in x equals 12 sevenths, 5 times 12 is 60 over 7, plus 2y equals 20, or 2y equals 20 minus 60 over 7, and 20 is 140 over 7 minus 60 over 7, which equals 80 over 7, and then dividing both sides by 2, y equals 40 over 7. Okay. So what is this point then? This point has x coefficient 12 over 7 and y coefficient 40 over 7, which is a little bit bigger than 6. So there's my region. Right? It's on the correct side of both of my two lines, and I found all 3 corner points. Excellent. So, having done that, we can move into a word problem, which is very similar. So, bakery makes 2 types of cake, flat cakes and layer cakes. Flat cake takes 30 minutes to bake, layer cake takes 45 minutes to bake, flat cake takes 20 minutes to frost, layer cake takes 15 minutes to frost, 360 minutes for baking, 210 minutes for frosting. So what are our constraints? And can we graph them as a system of variables and find a system of inequalities and find all corner points? So what are the 2 variables involved here? Well, they need to make cakes. So we'll say x is the number of flat cakes that we're making. And y equals the number of layer cakes that we're making. Okay, good enough. Constraints is a system of inequalities. Well, what are my inequalities here? Well, one is baking, right? I only have 360 minutes of overtime. I can't go over that. How much baking time do I need? Well, if I'm making X flat cakes and it takes me 30 minutes for each one, that means 30x. That's the time it takes to bake all my flat cakes. And if I'm making Y layer cakes, if Y is the number of layer cakes I'm going to take, that'll take 45 minutes for each one, so 45y. So this is the time needed to make the layer cakes. This is the time needed to make the flat cakes. That all has to be less than or equal to 360. The other constraint we have is that there's 210 minutes that my employees can frost things. Right? How much does each flat cake take to frost? Well, 20 minutes. How many am I making? X. So 20x is the number of minutes it takes for flat cakes to frost. And I'm making Y layer cakes. Each one takes 15 minutes to frost, so 15y, and I have 210 minutes for that. Great, so there's my constraints. But remember, we're actually making cakes, right? You can't have negative numbers of cakes. So the last 2 constraints, x is greater than or equal to 0, y is greater than or equal to 0. The number of flat cakes you make have to be 0, 1, or 2. It has to be something positive. The number of layer cakes you make has to be 0, or 1, or 2. That also has to be positive. Okay. Great, so there's our system of inequalities. Now we're just back into this problem, the previous 2 problems. Can you sketch these things? And you sketch them the same way, right? Your x-intercept here is 12, y-intercept is 8. Let me give myself a little space there. Right? I'm not going to go through all the data because it's pretty easy to do. And you shade the side. 0, 0 is on once you do your test point. For this one, your x-intercept is 10.5. Y-intercept is 14. And shade the side 0, 0 is on. Okay, so if we graph this, if we call this, say, 15 here, 14, 13, 12, 11, this would make this 10, 9, 8, 7, 6, 5, 6, 7, 8, 9, 10, yep, 4, 3, 2, 1, 0. So there's where my origin is going to be, and we'll go down one more line, and then we'll come out here. And our x-intercepts were 10.5, 1, 2, 3, 4, 5, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, so this must be 10, 11, 12, 13, 14, 15. Okay, so this line is x-intercept 12, y-intercept 8, so 12 and 8. And that is my baking constraint. So it's going to be, we shade this side. The other line, the frosting constraint, x-intercept is 10.5, y-intercept is 14, so there's 14, 10.5 would be about there. And there's my frosting constraint. And let's see if we can insert a little space here again. Good. Okay. And we want this side of the frosting line, right? Towards 0, 0. So this is my area that I'm worried about. And this is called the feasibility region. Feasibility. And what does that mean? What does that region mean in this context? Well, my x-axis, right, is number of flat cakes made. And my y-axis is number of layer cakes. This region here is combinations of flat cakes and layer cakes that I can make given my constraints, right? If I wanted to make one of each, well, I have enough time to do both of those. If I want to make 5 flat cakes and 10 layer cakes, well, that's outside of the feasibility region. I wouldn't have enough time to do it. So this area here represents the combinations of cakes I can make, the production schedules that I can actually make to get it to work. So what are my what are the boundaries of the feasibility region? Well, the baking constraint has the x-intercept, y-intercept of 8, right? The baking constraint, so 0, 8. I could make 8 layer cakes, right? And no flat cakes at all, and that would give me exactly 360 minutes of baking, but it would also give me 120 minutes only of frosting, so I'd have some frosting time left over. The frosting line has the x-intercept there, right? And the frosting line x-intercept is 10.5. So I could make 10.5 flat cakes, and that would use up all of my frosting time, but I'd still have some baking time left over. Of course, one corner is 0, 0. I could make nothing, and that would also is feasible. And then this here, this is where I'm actually using all my baking time and all my frosting time. It's on the intersection of 2 lines. So what is this intersection point? Well, again, 30x plus 45y equals 360, and we want to match the coefficients. And we'll multiply by 3. Because if I multiply by 3, that'll make this 45. And so by multiplying by 3, we get 30x plus 45y equals 360. And then 60x plus 45y equals 630. Subtract the top from bottom. And what do you get? You end up with 30x equals 270. So x equals 9. Plugging that back into one of these equations will get you y equals to 2. So if I make 9 flat cakes and 2 layer cakes, that'll chew up all the time that I have available. Okay. So this is my feasibility region. These are the corners of my feasibility region. And we're going to finish this little lecture up by looking at example 3 continued. Suppose you have a profit of $5 for each cake sold on flat cake. So each flat cake you sell gets you $5, and each layer cake you get gets you $5. So if they sell 5 of each type, they make $50 in profit, right? Because $25 for each one, so that's 50. Sketch this profit line on the graph. And so what is this profit line? Well, the profit function is 5 times x plus 5 times y. Here we're setting profit equal to 50. And so this is the $50 profit line, right? And we can sketch that on the graph of the inequalities above. So we'll take this graph here and just redraw it a little tidier. Well, a little. Right. So if we put the origin here, 1, 2, 3, 4, 5, 6, 7, 8. There's 1. This is my x, y's are my layer cakes. Number of layer cakes I make. And then 10.5 is the other corner point. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10.5, comma 0. That's another corner point. And then we're left also with this corner point, which is 9, 2. So 9, 2 is right there. So our region looks like that, and this is 0, 0, 9, 2. Okay, so this is our feasibility region. This is in green. So inside this area is all the combinations of cakes that I can make that can work out. So 50 equals 5x plus 5y. My x-intercept is 10. My y-intercept is 10. So let's do this one in red. My profit line will be x-intercept of 10, y-intercept of 10. And so this is profit equals $50. Is it possible for me to make $50? Sure, right? Any combinations of cakes that line the line here will get me exactly $50, and there's a bunch of them that I can actually make. Right? So, is it possible for them to make more profit? Well, if you sell no cakes, then you're making $0. So this is more profit, is on this side. P greater than 50. Less profit is on the other side. So there are combinations in here of cakes that I can make, because they're inside the feasibility region, that will get me more profit, because they're on this side of the profit line. So suppose we look at the profit line for P equal to 100. Okay, so we'll go back to black. For this one, we want to set P equal to 100. That becomes 100 equals 5x plus 5y, or x-intercept now is 100 divided by 5, and that's 20. Y-intercept becomes 100 divided by 5. That's also 20. And unfortunately, I didn't make my graph big enough to be able to put 20s on it. If we go back to my red line, we'll just pretend that it's out here somewhere. This is the profit equals 100 line. And the profit is, more profit is out this way. Right? That's P greater than 100. If you take a test point of 0, 0, and you plug it into here, you get 0 is actually less than 100, so 0, 0 is on the less than profit side. Right? So every line splits the plane into more and less. More profit is out this way, less profit is out this way. What's the maximum profit you can get? Well, you can make 50. You can't make 100 because there's no combinations of points on this line that are actually in the feasibility region, so you can't make $100 in profit. So where's the profit? What's your maximum profit going to be? It's somewhere between 50 and 100. And what's the relationship between these two lines? The profit equals 50 line is 50. Oops. We'll bring that out here. 50 equals 5x plus 5y. The profit equals 100 line is 100 equals 5x plus 5y. Note, slopes are the same. These are parallel lines, right? This line and this line are the same, because what's the slope of a line that's in standard form? Well, it's minus a over b. So the slope of this one is minus 1. The slope of this one is minus 1. So what's the effect of asking yourself about changing the profit from 50 to 100? Raising the profit that you want just moves this line out. right? So the profit equals 75 line, for example, is between these two and parallel to them. And so then that can let us answer the question of what's the maximum profit you can make. If you start raising the profit, right, the profit equals 51 line, for example, would be right parallel to this, but just a little bit to the right. And it would go through here, there's into the feasibility region. As the profit increases, the line goes out this way. What's the last point that it touches? Well, it's that vertex, that corner point. So the profit line through the corner point x equals 9, y equals 2 is the max profit. And so P equals 5 times 9, because you get $5 for each layer cake, plus 5 times 2, that's $55. So the maximum profit they can get is 55. So this is why we really need to be able to find these corner points and these regions, is because we want to be able to look at costs and say this is a feasibility region. I have costs that provide limits to how much of things I can make, and then I want to know, well, where's the maximum profit? And the interesting thing about where the maximum profit is going to be is that it will always be at a corner point. It won't necessarily be at this one, right? If the relative profits were different, you might find that one or that one as